So today we're going to talk about particle equilibrium. So just some definitions. Equilibrium is when a particle is at rest and will remain at rest. It can also be used in the context where a particle isn't undergoing acceleration, so at a constant speed, but in most statics problems, the particle is at rest. Coplanar force system is where all component terms cancel to have no force and thus no acceleration. So this means that there will be no net force in the system and no net acceleration once all of the force and acceleration vectors are added. So just some support types that you might see in technical drawings and diagrams. A pin support allows rotation, no translation though. So you can see that in the diagrams below. So this would be something like on a teeter-totter or seesaw, for example, there's a pin support where you can't translate the teeter-totter back and forth, but you can rock it on that pin support and rotate it. A roller allows translation on one axis and rotation, so this would be like a typical roller, or it can also be, for example, a block of synthetic rubber, which is sometimes used in bridges for expansion purposes, which only allows for translation one way or the other. And finally, fixed support, fairly simple. It provides no rotation or no translation, so it'd be kind of like, gluing two blocks together or something like that. So a procedure for particle equilibrium problems. So first we want to draw a free body diagram. Then we want to label the important points and give coordinates for those points. Then we want to find the position vectors for the points. Then we want to go position to force. So we did that, I think the last video, or maybe the one before, where we use the unit vectors and multiply it by the force. Then we find the equations for each component and equal them to 0, because of course each component is not moving in any way, so it would be equal to 0. And then create equations for the forces according to the component equations. So in this we just take those component equations and relate the different forces to each other. And finally, we want to solve for the forces using those equations. So we're going to start with just a quick example. Actually, this one is a bit more in depth. So we want to solve for the forces in each of those ropes. So that would be AD, BD, and CD, where A, B, and C are the points on the plate. And these ropes are supporting a 1,600 kilogram plate. The coordinates are given and a diagram is drawn. So really we can skip the first two questions, or 2 points on the procedure. Just to note that A and B are on the corner of the plate, and C is on one of the middle of the edges. So there is also an extra example, which is a bit more trivial, but first we'll go over this example here. So I've already laid out the position vectors. So I think we did this in one of the first videos of the statics. And essentially all we have to do is take the point minus the origin. So here the origin is D. And so, for example, if we take A minus the origin, would be 1040 minus 0. So we end up with the same thing. So we can do that for all of these. So A, B, and C for all the ropes. And then what I did was I found the unit vectors. So again, we've sort of gone over that, but just a refresher, we want to take all of these and divide them by the sum of them squared, square rooted. I'm sure you know what that looks like though. So another thing I did here was I negated them, and there is a reason for that, is because if you have a rope holding something up, so say this is A, point B, then the position vector for this will be sort of down and to the right, but the force vector for it, the tension vector, will be the opposite. So it'll be up and to the left. So that goes along with this step here, sort of the position to force. Just because we know that the force is tension, so it'll be going up like that. Okay. So once we have those, then we'll start looking at the components. So for the x component, we know that it's 0 because it's not moving, as with all the other components, since it is a statics problem. Let's say negative 0.3172 force A plus 0.3172 force B. And of course, this is just coming from these up here. So we can see that the only component in the x, or I, is our A and B. So then we can sort of relate them to each other, and we can say so 0.3172 FA equals 0.3172 FB, which means that FA is equal to FB. So that's an important relation for us to have. So we'll do the same with the y components. Oops. So y, it's a little bit more trickier because the force on the rope DC is included as well. So all I have to do is just add up those. So we'll put these in. Sorry, that should be a plus there. And again, we want to be working with those unit vectors at this point, just because they are the force vectors multiplied by the unit vectors. So then we can replace either FA with FB or FB with FA. And in this case, I'll just replace FA with FB. It doesn't matter which one. And that comes from this relationship that we just found. And then we can solve. So we can add those two FBs together and then find the relationship between FC and FB. So we'll find that 0.5273 FC equals FB, which you'll find if you solve for FB. All right, and then we're going to do the Z component, and this one is a little bit trickier, more so, just because there's one more component involved, which is the force of gravity. So I'll say that 0 is equal to and we can further simplify this by, again, replacing FB with, or rather FA with FB. So if I do that, I'm going to just skip a step here. So instead of substituting it in, I'll sort of do it directly. So 0 equals, let's see here. mistake again. Sorry, that should be minus, of course, because gravity's down, so Fg. And then from our relation that we found between Fc and Fb, we can do this. So replace Fb with that relationship from the y component, which we found was 0.5273 Fc plus and we can replace that, so that'll end up with 1.884, oops, 49 Fc minus Fg. Now, one thing that we can do now is find Fg, at least the, since it's only acting in one component, then we only really need to find the magnitude, since it's only acting down. So Fg equals mg equals 1600 kilograms times 9.81 meters per second squared, which is all equal to 15,096 newtons. And then we can solve for Fc. So we say therefore Fc equals 8,326.79 newtons, and then going back and using those relationships. So then Fb be equal to 0.5273 Fc, which is 8326.79, which is equal to 4390.72 newtons. And Fa is equal to Fb, which is equal to that same. Okay, so that is how you solve one of those questions. And just a note that, of course, these tensions are only magnitudes. So you could, just like we saw a few videos ago, you could take the tensions, the forces, and multiply them by the unit vectors. I'm not going to do that, but you could do that just to get the tension, in terms of directions and whatnot. So thank you for watching. Again, thank you to Loom and Google Keep, and as well to my professors. I hope this helped, and we'll see you in the next video.